Bam! Mr. True. Okay, in our first lesson that I might be hopefully get out of 2 today, we're going to be talking about graphing parametric equations. Do we remember the difference between graphing a pair of parametric equations versus the graph of just a function? Perfect, that's what we're reviewing. Okay, so when you graph a function in rectangular form, our sort of more common standard form, you're drawing a picture, a path through the two-dimensional coordinate plane that just includes all the coordinates, I'm pointing to these, but all the coordinates that satisfy a given rectangular function, where you plug in the x and y and the two sides are equal, right? You know, graphing parabolas and lines and such. When you graph or create a graph from a pair of parametric equations, now parametric equations are when you have two equations that create a single graph, but you have an equation that tracks horizontal movement and an equation that graphs or tracks the vertical movement. You have a parameter which is going to be not time per se, but it is a variable that tracks the sequence in which the points are created. So when you create a graph from a pair of parametric equations, not only do you have two equations that together work together as a team to create a single graph, but you get a direction of movement. You're tracking your movement over time. So the difference between a graph that has been created through just here's a function or an equation, create the graph, and here are a pair of parametric equations, create the graph. This will have some little arrows in the sketch or graph of the if I say function, I just mean equation. They can be relations too, that direct the movement. So it's not just the path of movement, it's the path and the direction of movement. So this parameter t, and it's not always going to be t, sort of is a sequence of time. And it may not be, it may not be time as in like the movement of time, like in seconds or something like that, but a sequence of when or how the points were created. So we're going to be doing two examples, creating graphs, showing that path, showing that direction of movement, and we're also going to be writing these back into sort of like that standard rectangular form, or AKA eliminate the parameter. And one's going to be simple algebraic, and the other one's going to be, the second one's going to be involving trigonometry. How do you create graphs when you have no idea what they look like? The simplest, maybe not the fastest, but the simplest way of creating a graph is through a t-table. Only this, maybe we'll call it a W table, because there'll be 3 columns and not 2. So we're going to have a column for t, a column for x, a column for y, and maybe we have a negative value of t, just so even though we're calling it time, there may be sort of like quote-unquote negative values of t or negative time, but it won't be, obviously, we're not going back in time. We're not going to get younger. But maybe t is -1, 0, 1, and 2, and 3. And we're just going to plug these in, because I don't really know what this is going to look like. Without experience, you wouldn't know. So maybe I want more than just a couple of points. So when t is equal to -1, we have -1 plus 1 is 0. When t is 0, we have 0 plus 1 is 1. When t is 1, we have 1 plus 1 is 2, and so on and so on. So we now have values of x. So we have some horizontal movement. Same with the y. Pretty simple math here. We are doing substitution, and be careful. This is going to be, the value of t is -1. So it's all of -1 being squared, right? We're not doing -1 squared, because that would be -1. But all of -1 being substituted in for t, -1 times -1, of course, is +1. And so we have a y value of 1, and then 0 squared is 0, 1 squared is 1, 2 squared is 4, and 3 squared is 9. So let's graph the equation and see what it looks like, or make a graph from the pair of equations. So we are still making our graphs on that just sort of, rectangular coordinate system. We have an x-axis and we have a y-axis. We don't have a t-axis. So we're just plotting the x and y coordinates like you've been doing probably since like pre-algebra when you're graphing lines. We have 0, 1. So let me get a purple marker out. So we have the coordinate of 0, 1. We have the coordinate of 1, 0. We have the coordinate of 2, 1. Of 3, 4. So over 3 and up 4. And finally, we have the coordinate of 4, 9. So from the origin over 4 and up 9, with experience that you two will start to remember from last year in pre-calc and then the year before that, hopefully from Algebra 2, when your horizontal component of your parametric equations, your x equals t plus 1, if that's a linear function, you can kind of like start to hypothesize what the graph probably looks like by just looking at your equation for y. But it can be very easy. You can have a pair of parametric equations and not really know what the graph is going to look like. So, but this is going to be a parabola. Now that's what I would do if I was just drawing a parabola in rectangular form. But one of these arrows is not really correct, is not really drawn correctly. And arguably I would say when drawing a graph from a pair of parametric equations, try your best to avoid drawing any arrows at the end of your parabola. Because arguably the domain's all real numbers, but this is just the path, say like of a particle in motion in space. This is just the path that particle is going to take. It doesn't indicate the direction. So the parametric part comes in, like how you show the variable of t in this x, y coordinate system is the sequence. The first point, now t is -1, but from going from low values of t to high, the first coordinate we came up with was 0, 1. So this is our first point. The 1, 0 was our second coordinate, our second point that we found. 2, 1 was our third coordinate. And that's really all you need to kind of start seeing that direction of movement. We are going from 1 to 2 to 3. As t is increasing from -1, 0, 1, 2, 3, and so on and so on, our first coordinate that we came up with our W table was 0, 1, and then 1, 0, and then 2, 1, and then 3, 4. This is how, I'm numbering how those coordinates came out of the t table. So our direction of movement, in this case, is left to right, which is sort of that standard movement that as we read graphs, but that's not guaranteed. Like you need to make this t-table to give you the path that say some particle is following, and then pay attention to how those coordinates came up to know the direction. These arrows will not always go left to right. And that's, that's how you create a graph from a pair of parametric equations. Now, our next example is going to be a little bit more complicated. So there might be a benefit, beyond just, oh, well, the direction's said to. But there might be a benefit to eliminating the parameter. Or you might very well have questions that I just simply ask you to eliminate the parameter. Well, in x is equal to t plus 1 and y is equal to t squared, eliminating the parameter, as it will in our next question, might allow you to create a graph from the parametric equations quicker. With a little bit of experience, you might see, oh, linear function, quadratic function, this is probably a parabola, and this number of points is sufficient. But if it's a bit more complex, the graphing process, the drawing process, may be sped up by eliminating the parameter. So for our next example, if you will, we're going to use the same equations, but we're going to eliminate the parameter. Now, I'm kind of forgetting that you all didn't have me for pre-calc. One of you did. But a lot of students don't initially like my teaching because I don't give steps. Oh, here's a problem, follow these steps. Here's a problem, follow these steps. Here's a problem, follow these steps. Because that prescribed nature of learning how to do math can really get you in quite a pickle. So this is a standard algebraic problem, and we can look at this sort of, call it a system of equations, and think about how did you solve systems of equations in Algebra 2 and in pre-calculus. You did, one of the processes you learned was substitution. And that's where you take one of the equations, so x is equal to t plus 1, solve one of the equations for one of the variables that's going to most benefit you through the rest of the process, and we want to eliminate the parameters. So I want a rectangular form of this parabola, like f of x or y is equal to something squared, right? No t. So I want to get rid of t. I want to solve for t and get x minus 1 is equal to t. And then through the variable of t, get the function that tracks the horizontal movement of our particle in space into the function or equation that graphs the vertical movement, and create a single function that relates y to x, right? Like we're generally used to with most math equations. So this expression of x minus 1 is going to go in for y, and we have y is equal to, well, instead of t squared, it's t, which is x minus 1 squared. And then now, see what you have here? If you remember any kind of transformations that I may or may not have taught you last year, you have a y is equal to some kind of x term or expression with x in it squared. So there's your indication that you're looking at a parabola. And then inside that math function, you have a plus or minus. This would be called a c in my notes for transformations. That x minus 1 is going to move our parabola to the right 1 unit. And our vertex doesn't have our parabola doesn't have a vertex 0, 0, the origin. It has a vertex at 1, 0, 1 to the right. And so knowing what this might be able to let you go, oh, these parametric equations is just a parabola shifted to the right 1. So here's my path of movement. And then maybe you only need to do a t-table with 2 values of t instead of what we did, which was 5. And that's the end of example 1. Okay? Keep in mind, we eliminated the parameter through substitution. Okay? That's going to be important in the next example. So for example number 2, we want to make a graph from these parametric equations. So we have x is equal to 8 cosine of theta, and y is also equal to 8, but this time sine of theta. Okay, so we have no idea what this graph is going to look like. And these are pretty complex equations here for our pair of parametric equations. I mean, it has trig in it. So if we want to make a graph from this pair of parametric equations, oh, and by the way, I meant to mention this on the first example. We are tracking horizontal and vertical movement. When you study vectors, vectors have a horizontal and vertical component, and vector v would be written as a times vector I plus b times vector j. AKA, in our review of parametric equations, which track horizontal and vertical movement, flow very nicely into reviewing and rebuilding your knowledge of vectors. And we'll be doing some very basic calculus of vectors coming up shortly, but very directly related. This is effectively kind of like a pair of parametric equations tracking that horizontal and vertical movement. Okay. So we're going to make a W table. We're going to make a T table with theta. Now here our parameter is not t. Most of the time your parameter is going to be labeled with that letter of t for kind of like t for time, but it can be other things. So in this case, our parameter theta is just our angle movements, going from some low to high number. So what would be the easiest angles to deal with around the unit circle involving sine and cosine? Yeah, the quadrantal angles. First one being 0, and then pi over 2, and then pi, and then 3 pi over 2. So our values of x coming from 8 cosine theta will be, what's the cosine of 0? 1 times 8. What's the cosine of pi over 2? 0 times 8. What's the cosine of pi? Negative 1 times 8 is negative 8. And then the cosine of 3 pi over 2? 0 times 8, which is 0. And then y is going to be 8 sine of theta. So what is the sine of 0? 0 times 8 is 0. Pi over 2, what's the sine of pi over 2? 1 times 8, so we have 8. Sine of pi back to 0 times 8 is 0. And then the sine of 3 pi over 2 is negative 1 times 8, or negative 8. If I've never done this question, never graphed a pair of parametric equations that involve trig, who knows what this graph looks like? It's, by the way, not going to be a function. So if I say the word function, just, it's a graph, it's a relation. So 4 points is very likely really not enough to make a good graph. I would like to eliminate the parameter to get a better idea of what this graph is going to look like. And then I'll just use this table of values to know what direction the movement is in. So I always love doing this in pre-calc, and only one of you had me for pre-calc. So let's do this from scratch. We have x is equal to 8 cosine of theta. And let's solve this system of equations. Let's get information about the horizontal movement into the equation tracking the vertical movement through substitution. Okay? Like, oh, well, I want to solve every question involving parametric equations through one step. You know, give me some steps to follow. Okay, take one of the equations and solve it for a variable, assuming the, you know, so you have y in terms of x. Take the equation for x and solve it for the parameter. How do we solve this for theta? Divide by 8, right? I'm going to turn this around too. So we have the cosine of theta is equal to x over 8. How do we get the theta out of the cosine function? Inverse cosine. So then theta is equal to arc, you can say inverse cosine too, but I'm going to say arc cosine of x over 8. And then now that we know what theta is equal to, and over here we have y in terms of theta, we can say that y, we're doing the substitution part now, y is equal to 8 sine of arc cosine of x over 8. Well, the whole point of eliminating the parameter, and by the way, is there any theta left? No, so we have eliminated the parameter. Done. But the point of this was to be able to come up with an equation, or hopefully have a sort of regular rectangular function, rectangular equation, stop using the word function, that will help me draw a picture of this situation. And yeah, that ain't going to happen. Now, for probably, I hate to say this, but I'm going to say it on camera because, you know, we're always learning, even if we're supposed to be the experts. If it were pre-calc, we would have already done, I'm looking at like the example one still over there. We would have done 2 or 3 examples of eliminating the parameters through substitution, and then we would have gotten through here and I'd be like, this is disgusting, this is gross. We need to just go back and start over again and show another way of eliminating the parameter that's more efficient. But, you know, now I teach calculus and I teach higher level math and in IB, and it was really that course that where they make you really make you see the connections with all the things you've learned over your years of middle school and high school, all math, you know, and link them together, not to get stuck and give up when things get hard. We can simplify this function so that there is no trig in it. So, how did I start nearly every question in trig last year? With a picture. Woo! Oh, that was lame. There we go. With a picture. And what do you put into a trig function? An angle. What do you get out? Sides of a triangle. So that's all trig is a study of. Rotation and little right triangles, which are the reference triangles. The little acute angle between the terminal side and the x-axis. So we have the sine of arc cosine. What do you have to put into sine? It is just a trig function. What goes into a trig function? An angle. So this arc cosine has to be giving you an angle measure because that's what you put into sine. And this is an inverse trig function. What do you know about inverses? The role of x and y, the role of domain and range, swap. So if a trig function is angle in, parts of a triangle out, then an inverse trig function is parts of the triangle n. Now, we'll have to erase this later, so I have some room. But when you see arc cosine of x over 8, you need to realize that that x over 8 is parts of a reference triangle. Not a regular triangle, but a right triangle. So we're going to draw an angle in quadrant 1 for convenience. We're going to draw a reference triangle against the x-axis. Cosine SOHCAHTOA, TOA, cosine, or actually I can point over here, cosine of theta is adjacent over hypotenuse. So the adjacent leg is x, the hypotenuse is 8. And when you do finish the Pythagorean theorem, x squared plus, I don't know, b squared is equal to c squared. We have b squared is equal to 64 minus x squared, and b is the square root of 64 minus x squared.
Wait, Mr. Travis might be stupid.
Oh, please don't tell me this is
No, you didn't. It's just me. Because this is arc cosine, like, why is 8 not the adjacent position?
Because the cosine of theta is the adjacent leg over the hypotenuse. And sine of theta, which we're about to use, is the opposite leg over the hypotenuse. And if you wanted to see tangent, just because you're asking that question, tangent is opposite over hypotenuse. And if we were doing a bunch of unit circle questions, this is not reciprocal, right? Inverse trig functions are not reciprocals. I finally started to realize why you were probably asking. And if you're doing a bunch of trig work on unit circles, we memorize these formulas as cosine of theta is x over r, sine of theta is y over r, and tangent of theta is y over x. But inverse functions are not reciprocal functions. Those are very different ideas. Vocabulary that's also very commonly kind of messed up a little bit. So what do we get from arc cosine? An angle. So our next line of work is y is equal to 8 times the sine of an angle. Well, we still have trig in this equation. So then we have y is equal to 8. What is the sine of theta? Opposite over hypotenuse, or the square root of 64 minus x squared. Does this look at all familiar to you like trig substitution, integration by trig substitution? We're going from trig to algebra. Oh my gosh, it like all connects. I'm so much more awake than I was 2 hours ago, yay. Okay, so what happens with our 8s? They cancel. I'm also not going to finish with as many topics as I would like, but that's okay. Come on, erase, please. So now we've got, this purple doesn't like to erase. So now we've got y is equal to the square root of 64 minus x squared. You may not recognize what that looks like from Algebra 2 or Pre-Calc, unless you did a lot of conic sections work recently. So maybe we square both sides and get y squared is equal to 64 minus x squared. And then if you add x squared to both sides, you have x squared plus y squared is equal to 64. And you're like, oh, I've got a circle with a center of 0, 0, and a radius equal to 6. 8.
What? I was like, wait, now you know.
Okay, first mistake of this period of 8. So we've got, that was pretty good. We've got a circle, and over there from way back in the time machine when we did our t-table, the first coordinate was 8, 0. The second coordinate was 0, 8. The third coordinate was negative 8, 0. So actually, I did not make this graph from the parametric table, I made this graph from the algebra. But the parametric table is going to tell me that this is the direction of movement. Now, this is a very complex way of eliminating the parameter. You do not eliminate the parameter. You do not eliminate the parameter this way unless you really know your trig. Now, you still have to know some trig to do this problem, but we kind of got into the weeds by doing the substitution method. We had to remember that what do you put into a trig function? An angle. What do you get out? Sides of a triangle. And we had to remember how to inverse trig functions work. And we had to draw that little diagram that I guess I erased up there. How can we get to that equation much, much faster? By using something called the combination method. When you were in Algebra 2, in Algebra 1 and Algebra 2, when you were solving linear systems of equations, you learned linear combination. These are not linear functions, so that's inappropriate to say, but the combination method and substitution. We have two equations with a sine and a cosine. Do we not have a trig identity that relates sine and cosine together? Sine squared theta plus cosine squared theta is equal to 1. So I could take these two equations and isolate the sine and cosine. I am going to need this room. So x over 8 is equal to cosine of theta. Y over 8 is equal to sine of theta. Square both sides. And I'm going to stack these so we can add them. And we're going to have x squared over 64 is equal to cosine squared theta. And y squared over 64 is equal to sine squared theta. And now when we add these two equations, we get x squared plus over 64 plus y squared over 64 is equal to sine squared theta plus cosine squared theta. But what's sine squared theta plus cosine squared theta? An expression that has our parameter of theta. It's equal to 1. Now, you might recognize this as, and probably not unless you've studied conic sections recently, but you might recognize this as an ellipse. So you have an ellipse where the major and minor axis will have the same length. They'll both be 16 in total. Or you can take this and multiply both sides by 64 and move it into, a circle is a special type of ellipse, and then boom, still there's your algebraic equation and helping you to come up with the graph.